let's discuss about circle. In algebra, there are so many things that we could graph that there is one class of figures called conic section that will be very important. First, let's learn what this term means. Take this three-dimensional right circular double knot cone. We can create different two-dimensional figures by taking a plane and swiping through the cone in different ways. If the plane goes from one side of the cone to the other and is parallel to the base, we get a circle. If the plane does the same thing but is not parallel to the base, we get an ellipse. If the plane cuts from the side of the cone down to the base, we get parabola. And if the plane cuts all the way from one base to the other, we get a hyperbola. So, these are called conic section because they are literally different cross sections of a cone. We can also describe this using a parameter called eccentricity, which is a term that describes how much a conic section deviates from being perfectly circular for a circle. This value is 0. For an ellipse, it's between 0 and 1. For a parabola, it's precisely 1. And for a hyperbola, it's greater than 1. Let's learn how we can graph these different figures, one at a time, starting with circles. As we know, circles are defined as the set of all points in a plane that are equidistant from a fixed point, which we refer to as the center of the circle. This distance from the center to any point in the circles is called the radius of the circle. If we place the circle in the coordinate plane, we could say that any point on this circle has coordinate of x and y because any point in the circle contains x and y values that satisfy the conditions of the circle. If we can also label the center as the point hk, so how can we algebraically represent the set of points in the circle? Well, we just learned how to use the distance formula that looks like this. And it says that when we examine any 2 points in the coordinate plane, the distance between them will be the square root of the difference between the x values plus the square of the difference between the y values. This applies here because any point on the circle has coordinate x, y, and the center, which is what we are measuring the distance from. Well, calculus BHK. So, we get the square root of x minus h quantity squared plus y minus k quantity squared. For any x and y value that satisfy this expression, we get some radius of the circle represented by r. All we have to do is square both sides and we get the standard form for the equation of a circle with 3 terms and squared. We can use this and understanding to graph a circle given an equation. Let's start with something simple like x squared plus y squared equals 9. In this case, there are no h and k terms, so h and k must both be 0, meaning that the center of the circle is at the origin. Then r squared is 9, so the radius must be 3, and there's our circle. Now let's look at one with h and k terms present. Here, the only thing we have to remember is that it's x minus h and y minus k. So, if we have x minus 2 and y minus 3, the center will be at 2, 3, both positive because h equals 2 and k equals 3. According to the equation, if we had x plus 2 and y plus 3, that would be the same as x minus negative 2 and y minus negative 3. So in that case, the center would be at negative 2 and negative 3. So we can also go the other way around and derive the equation of a circle from its graph. Look at this one here. All we need to do is locate the center to get the h and k values and then find the radius. This is easy if we just go in a direct horizontal or vertical direction from the center and see how far it is to a point on the circle. Don't forget to square this since we need r squared. So this will be the equation for this circle. A lot of circles will have graphs and equations that are this simple, but sometimes we have to get clever. Say we have something like x squared plus y squared plus 4x minus 6y minus 23. If you look carefully, we will notice that this can be rearranged to be put into standard form. We can just bring 23 to other side and then group the x and y terms separately. We learned how to compute the square, and that's exactly what we will do here, but y is one spare variable. We simply notice that for the x term, we can add 4 to get a perfect square, making sure to add 4 to the other side as well. And now this term can become x plus 2 quantity squared. We can also see that for y terms, we have to add 9. Again, making sure to add to the other side as well. And again, we have a perfect square which allows us to express this as y minus 3 quantity squared. Add up the numbers on the right and we've got a circle in standard form, with its center at negative 2, 3, and with a radius of 6. So now, we know how to represent graphically, how to write the equation in standard form, and how to manipulate an equation in order to get it into standard form. So that we can graph it, circles are relatively simple compared to the other conic section. So that would be all for this topic.